All right, thank you very much. I'm going to turn us back to yesterday when we talked a lot about planet formation and the importance of understanding the role of volatiles in seeding the giant planet. In particular, understanding the carbon to oxygen ratio is very important for determining how and when the giant planets received their inventory of heavy elements which contributed to their growth. And I'm going to talk about how we find that information for Jupiter, which isn't from JWST, it's from the Juno mission. But then I'm going to talk briefly about exogiant planets and compare the carbon to oxygen ratio we have from Jupiter to that for a few exogiant planets. So yesterday and on Tuesday, we talked a lot about carbon to oxygen ratios and how they change in protoplanetary disks. The figure on the lower left is a redrawing of the one from Oberg et al. In 2011, showing how the carbon to oxygen ratio in grains and gas in protoplanetary disks change as material moves through snow lines, so the water, the CO, and the CO2 condensation fronts. The lower right-hand figure is an example of how dynamics may work with these snow lines to set up very complicated variations in the carbon to oxygen ratio. It's from a paper by Muzis et al. And what it shows in a conceptual sense is the radial drifting inward of pebbles. Those are small solid bodies that are affected by gas drag in the protoplanetary disk. And if those pebbles are loaded with volatiles, CO, N2, CO2, and so forth, as they pass through the region where amorphous ice is converted to crystalline ice, then poof, the volatiles are released into the gas phase because the crystalline ice cannot hold as much volatile material as amorphous ice can. And if at that point the water itself does not move inward and evaporate further, that is, if a giant planet forms outward of the snow line, you can end up with a situation, as Andrea Benzotti described yesterday, where you could trap the water planetesimals, now the volatile pore planetesimals, and accrete gas that is rich in carbon-bearing materials and enhance the carbon to oxygen ratio that way. So does that happen in giant planets? Did it happen in Jupiter? To understand that, we have to know how much carbon and oxygen is present in Jupiter. And that turns out for the oxygen to be a very difficult problem. For the carbon, it's not, because methane is not a condensable in Jupiter's atmosphere. Methane, which is the dominant carbon-bearing species, has been measured spectroscopically and also by the Galileo probe, which measured it directly in situ with a mass spectrometer. And that is a solid number that is between 3 and 4 times the solar value. Oxygen, on the other hand, is principally in the form of water in Jupiter's atmosphere, and water condenses out in the visible atmosphere of Jupiter. And so the Galileo probe was designed to plunge down to below 20 bars pressure. It was thought that anything below 10 bars would not be affected by the formation of a water cloud. I was going to point out rain outside, but it stopped raining, so that's not a good example. But there are some water clouds out there still. So the graph on the lower left is the water mixing ratio as measured by the Galileo mass spectrometer in situ in 1995 versus atmospheric pressure in bars. The solar abundance of water is shown by the horizontal line. And what was thought to be the base of the water cloud is shown by the vertical line for a solar abundance of water. If water were 3 times solar, that vertical line would slide to the right to about 8 bars pressure. And what you see is that between 10 and 12 bars, the Galileo mass spectrometer measured a very low abundance of water. So one might say, well, that can't be due to condensation. Maybe it's the very process that we just talked about. Maybe water planetesimals were excluded from Jupiter. But then at 20 bars, the Galileo probe measured a somewhat larger abundance of water, but still subsolar. So evidently something is going on in the dynamics of that region of Jupiter that the Galileo probe visited that has affected the water abundance, and we cannot get a global bulk oxygen abundance to compare with carbon from those data. So the Juno mission was proposed and conceived in part to address this issue. It was designed to carry with it a microwave radiometer to measure the water abundance globally, but to do so at pressure levels well below the cloud. Microwaves, of course, as we know from our microwave ovens in the sort of 10 to 15 centimeter wavelength region, are very effectively absorbed by water. And so the brightness, temperature, or emission in the microwave would tell us what the water abundance is. You can't really do this from Earth for Jupiter because Jupiter's synchrotron radiation essentially blinds that signature. And so the idea of Juno was to bring a spacecraft very close to Jupiter, under the radiation belts, and do those measurements from 1 to 50 centimeters wavelength. So what I've done is to draw here in a very artistic way the pressure levels at which Juno makes that measurement. So the microwave radiometer, which you see in the red circle there, was designed actually to measure down to hundreds of bars, but the water measurement is principally done down to about 100 bars. Now, the microwave radiometer has worked very well, but it's still difficult to get the water abundance because the other major microwave absorber is ammonia. And the assumption that we made in proposing Juno was that below 10 bars, ammonia would be a constant. Ammonia has turned out not to be a constant. In fact, it varies with depth down to several tens of bars. And the interpretation of that is in that little cloud cartoon that you see there, which is that ammonia and water together are forming very, very large, essentially hailstones, which gradually melt. We call them mush balls. This was an idea originally by Tristan Guillot. And as they fall through the base of the cloud, they gradually evaporate, releasing ammonia into the gas phase. And that is what is seen in the microwave radiometry data. So that affects the ability to determine the water abundance. Further, we don't know a priori the physical temperature profile in that part of the atmosphere. That also comes from the microwave data. And so determining the water abundance becomes a very complex problem. And so in addition to the microwave radiometer, Juno data that involves observing lightning, that provides us a constraint on water. Juno data that measures other species that carry oxygen, like carbon monoxide, which are sensitive to the oxygen abundance, particularly in the very, very deep atmosphere, have been measured both from the Earth and also other trace species that help us in using this to determine the oxygen abundance, like germane and arsine, have actually been measured by the GIRAM instrument on Juno. And then finally, we get a limit on the abundance of heavy elements by mapping the gravity field of Jupiter with Juno. That's a very precise measurement that allows the mass distribution inside of Jupiter to be determined, and therefore the abundance of heavy elements, provided that you know the behavior of these materials at very, very high pressures, millions of atmospheres pressure, so you have to know the equation of state. That turns out to be the limiting accuracy here, the limit on the accuracy. So I'm not going to show any of the data because this is a very short talk. It was blood, sweat, and tears to try to get a water number. What I'm plotting here is the oxygen abundance, O over H, relative to the solar value. So 1 is solar, as determined now from the microwave radiometer, that's on the x-axis, from lightning observations using a model that Yuri Agliamov, my student at Cornell, put together. He's now a postdoc at Michigan. Disequilibrium species, essentially here, the abundance of carbon monoxide is observed at the 1 bar level is determined by its chemical interactions very deep down at about the kilobar level. That's work that's been done by Cavalli et al., and then the interior data. And when you put all these together, a fully consistent water abundance is given by the gray barred region that you see there. Now, the microwave radiometry data has a fairly large potential range, but what's crucial is that the lower limit of the water is 1.5 times solar. And that's important because the gravity data limit us to a heavy element abundance, which we assume to be both oxygen and carbon, that gives an oxygen abundance of 3 times solar. And the other determinations are in between. So a reasonable conclusion for the oxygen abundance, the bulk oxygen abundance in Jupiter, assuming that the interior and the atmosphere are connected to each other, is somewhere between 1.5 and 3 times solar. And in the paper that I submitted for this conference, I talk about an alternative where the atmosphere has been separately seeded by additional heavy elements. I'm not going to talk about that here. That corresponds with the Galileo determination of the C to O ratio of roughly a value between 1 and 3. So an oxygen and carbon enrichment relative to solar that are roughly the same, or a carbon enrichment that is as much as 3 times larger than the water. And that in turn, if you want to interpret this in terms of planetesimal seeding, really eliminates some particular types of planetesimals. Clathrate hydrates, which trap volatiles in crystalline water ice, would lead to too much water, probably adsorption as well. SIPs are solar composition icy planetesimals, essentially very cold planetesimals where all of the elements are condensed out, as proposed originally by Toby Owen and Therese Ankranaz, fit very well. The volatile release story would fit at the higher carbon to oxygen end. So I think this eliminates some potential alternatives. So how does this compare with exoplanets? So in my GTO program, which is 1274, in which I've collaborated with the group of Jacob Bean at the University of Chicago, we have 5 giant planets around other stars. We've analyzed 3 of them and published those. These are all transits. HD 149026b and WASP 77AB are secondary transits, so thermal data. And then HD 209458b, which has a little heart on it because a group of us wrote a paper about doing transits on this in 2001. That's a primary transit, so it's a transmission spectrum. All from JWST, all a single visit. So it's 2 visits, but for the 2 different parts of the spectrum, HD 149 and 209 are near cam, WASP 77 is near spec, and so each spectrum overall is the equivalent of just 1 visit, about 10 to 20 hours of time. So what are the results? The results are plotted here on a diagram that Nicole Lewis showed on Tuesday. It comes originally from Thorngren and Fortney. It's the enrichment of heavy elements relative to protosolar on the y-axis versus the mass of the object on the x-axis. There's a line, a diagonal line that's drawn, which is the solar system trend line based on Uranus, Neptune, and Saturn, assuming that their carbon abundances are actually the overall heavy element enrichment, that is, that oxygen and carbon are enriched to the same extent. Jupiter was a little bit above that line in the original diagram. The oxygen result that I've described here brings it down to that line actually pretty nicely. And the 3 objects that we've analyzed in the GTO program are shown there as well. The faint gray lines are the enrichments based upon HST and Spitzer data from earlier papers. You can see the improvement that JWST provides in terms of giving us enrichments with reasonable error bars that allow for an interpretation rather than just a limit. I'll point out that HD 209458b, that enrichment is larger than in previous results from Spitzer and HST. It's something we may want to talk about in the discussion. It falls right on the solar system trend line, which is very nice. But if you go to the C to O ratio, HD 209458b has a very low carbon to oxygen ratio. So I don't think there's a trend here. I think the lesson in this is that we have to look at many more giant planets to understand the trend as a function of their mass and perhaps position, stellar types, and so on. But this is just the beginning for JWST. So I'll summarize by, that's me saying stop. All right, so I will summarize here. We now from Juno, I think, have a reasonable value for the oxygen abundance between 1.5 and 3 times solar. Exoplanets fall above and below that. HD 209458b, also known as Osiris, does look like kin to our giant planets in terms of total metallicity, but not in terms of carbon to oxygen ratio. Thank you.